Look up. On a clear night, the sky reveals a tapestry of distant suns, scattered across the immense darkness of space. Among them, a few special points of light wander against the fixed backdrop of stars. These are not stars but worlds, planets, just like our own Earth. They are our cosmic neighbors, bound together by the gravity of our star, the Sun. This family of worlds, our solar system, is a place of staggering variety and breathtaking wonder. From scorching hot landscapes to frozen giants, each planet tells a unique story, a chapter in the grand narrative of how solar systems form, evolve, and perhaps even harbor life. It is a story that we are just beginning to read, and it has so much to teach us about our own place in the cosmos. Embarking on a journey through our solar system is to witness the incredible diversity that nature can produce. It is a voyage that takes us from a tiny, sun-baked rock to immense gas worlds with storms larger than our entire planet. We will see moons with underground oceans and others with lakes of liquid methane. These are not just abstract points of light, they are tangible places, with weather, geology, and histories all their own. Understanding these worlds helps us piece together the puzzle of our own origins. We learn that the conditions that allowed life to flourish on Earth are fragile and perhaps rare, a delicate balance of factors that went a different way on our planetary siblings. The story of our solar system is also our story. The scale of our cosmic neighborhood is almost beyond human comprehension. The distances are vast, measured in units so large they dwarf our everyday experience. Yet despite these immense gulfs of space, we have found ways to bridge them. Through the ingenuity of science and engineering, we have sent robotic emissaries to fly past, orbit, and even land on these distant worlds. These missions are our eyes and hands, extending our senses across millions of miles. They touch the soil of Mars, dip into the atmosphere of Jupiter, and analyze the icy particles of Saturn's rings. Each piece of data, each image sent back to Earth adds another brushstroke to the magnificent portrait of our solar system. This exploration is driven by a fundamental human curiosity, a desire to know what lies over the next hill or beyond the next horizon. We are a species of explorers, and the solar system is our current frontier. By studying these other worlds, we gain a profound perspective on our own. We see Earth not as an isolated island but as part of a grander, interconnected system. This journey is more than just an astronomical exercise, it is a journey of self-discovery. It forces us to confront the biggest questions we can ask. Are we alone? What is the fate of our world? And what does our future among the stars look like? The answers await us out there, in the silent, swirling dance of the planets. Our journey begins with the innermost planet, Mercury. It is a world of extreme contrasts, locked in a tight, swift orbit around the Sun. Being the closest planet, it endures a relentless solar bombardment, with surface temperatures soaring high enough to melt lead. For centuries, it was a difficult world to study, its faint light often lost in the glare of the Sun. Observing it from Earth is a challenge, and even the mighty Hubble Space Telescope is forbidden from looking its way to protect its sensitive optics from the Sun's intense radiation. Mercury holds its secrets close, but what we have learned has been truly astonishing, revealing a world far more complex than a simple sun-scorched rock. One of the most surprising discoveries about Mercury is the presence of water ice. This seems impossible for a planet where daytime temperatures can reach over 800 degrees Fahrenheit. The secret lies in the planet's tilt. Mercury's axis is almost perfectly upright, meaning it has no significant seasons. At its north and south poles there are craters whose floors are permanently shielded from the sun's rays. These cold traps are some of the coldest places in the entire solar system, perpetually locked in shadow. In these frigid pockets, scientists believe 1 trillion tons of water ice have persisted for billions of years, likely delivered by impacting comets and asteroids long ago. Beneath its cratered surface, Mercury hides another profound anomaly, its enormous iron core. Relative to its size, Mercury's core is unusually large, making up a significant portion of the planet's mass, leaving only a thin, rocky mantle. This is vastly different from Earth or Mars. This strange composition suggests that Mercury had a violent and dramatic past. Early theories proposed a cataclysmic head-on collision with another large body that stripped away most of its original rocky crust and mantle. The planet we see today may be just the battered remnant of a once much larger world, a survivor of a cosmic hit-and-run that forever altered its destiny. How did this happen? The evidence gathered by NASA's Messenger spacecraft, which orbited the planet from 2011 to 2015, points to a more nuanced story. The probe found volatile elements like potassium on the surface, which should have been vaporized in a high-heat, head-on impact. A newer theory suggests a hit-and-run collision, where a proto-Earth or other large object delivered a glancing blow. This impact would have been powerful enough to strip away the mantle, but not hot enough to boil away all the volatile materials. This makes Mercury a key witness to the chaotic, early days of our solar system, a time of planetary billiards where worlds were built and destroyed. Next we journey to Venus, the second planet from the Sun. At first glance, it is Earth's twin. It is nearly identical in size, mass, and composition, and it is likely that billions of years ago, the two planets started out very similarly. They were born from the same cloud of gas and dust, and for a time their paths may have seemed parallel. Venus might have once had oceans of liquid water and a temperate climate, a world that could have been a cradle for life. But somewhere along the way, its evolutionary path took a dramatically different turn. Today, Venus is not a haven, but a hellscape, a cautionary tale of a paradise lost. The transformation of Venus was driven by a runaway greenhouse effect. The culprit was massive, prolonged volcanic activity that spewed unimaginable quantities of carbon dioxide into the atmosphere. This thick blanket of CO2, now extending 155 miles deep, trapped the sun's heat with terrifying efficiency. As the planet warmed, its oceans boiled away, adding more heat-trapping water vapor to the atmosphere and accelerating the process. The result is the most extreme environment in the solar system. The surface pressure is over 90 times that of Earth, equivalent to being nearly a kilometer deep in our ocean, and the temperature is a uniform 900 degrees Fahrenheit, hot enough to melt lead. The evidence of this volcanic past is etched all over the planet's surface. Radar maps, piercing through the dense permanent cloud cover, reveal a world dominated by volcanic features. There are tens of thousands of shield volcanoes, similar to those in Hawaii but far more numerous, dotting the landscape. These volcanoes were the factories that produced the planet's thick, toxic atmosphere. The clouds themselves are not made of water vapor but are laced with droplets of concentrated sulfuric acid. It is a world perpetually shrouded, its surface hidden from direct view, a testament to the powerful geological forces that reshaped an entire planet and sealed its fate. Despite the inhospitable surface, some scientists have not given up on the idea of life on Venus. The hope lies not on the ground but high up in the atmosphere. About 30 to 35 miles above the surface, the temperatures and pressures are surprisingly Earth-like. In this narrow, temperate zone there is solar energy, traces of water, and a soup of chemicals that could potentially serve as nutrients. It is a long shot, but it is conceivable that microbial life could have adapted to float in these clouds, a last bastion of biology on a world that lost its way. Venus serves as a stark reminder of how a planet so similar to our own can become so radically different. Our next stop is Mars, the fourth planet from the Sun, known as the Red Planet for its rusty, iron-rich dust. For centuries, Mars has captivated the human imagination as the most likely place to find extraterrestrial life. Its polar ice caps, changing seasons, and ancient canals, later revealed to be optical illusions, fueled dreams of Martian civilizations. Today, we know that Mars is a cold, dry desert with a thin atmosphere, its surface bombarded by deadly solar radiation. But the story written in its rocks and canyons tells of a very different past. Evidence from rovers and orbiters overwhelmingly points to a time when Mars was a warmer, wetter world, with rivers, lakes, and perhaps even a vast northern ocean. The Mars we see today may be the result of a catastrophic event early in its history. One leading theory suggests that about 4.5 billion years ago, an object the size of Pluto slammed into the planet. This colossal impact would have created the Borealis Basin, a gigantic crater that covers 40% of the planet's northern hemisphere. The energy from this collision could have melted the surface, blown away a significant portion of the atmosphere, and boiled its oceans, effectively sterilizing a world that might have been on the cusp of developing life. Mars never fully recovered from this blow, slowly losing its remaining atmosphere and water to space over billions of years. This tragic history does not mean the hunt for Martian life is over. While the surface is hostile, life might still cling to existence in protected niches underground. Scientists are now looking for it in places shielded from the harsh surface radiation. Ancient lava tubes, tunnels formed by flowing magma, could provide stable temperatures, moisture, and protection. Another promising location is between sand dunes where digging down might lead to a hidden water table, similar to how life finds water in Earth's driest deserts. If life exists on Mars today, it is likely microbial and hidden deep beneath the ruddy dust, waiting to be discovered. The search for life on Mars carries a fascinating, if controversial, implication for our own origins. The theory of panspermia suggests that life can travel between planets, carried on meteorites. The enormous impact that scarred Mars would have blasted trillions of tons of rock into space, and we know that some of these Martian meteorites have landed on Earth. It is a mind-bending possibility that the late heavy bombardment that peppered early Earth was seeded with debris from Mars. Could it be that life on Earth was actually born on Mars, and traveled here as a refugee from a planetary catastrophe? We may, in a very real sense, all be Martians. Leaving the rocky inner planets behind, we cross the asteroid belt and enter the realm of the giants. Our first destination is Jupiter, the undisputed king of the solar system. This gas giant is a world of superlatives. It is more massive than all the other planets, moons, and asteroids combined. You could fit over 1,300 Earths inside it. Jupiter is so large it's almost a failed star. As it slowly cools from its formation billions of years ago, it actually radiates more heat into space than it receives from the distant sun. This internal heat engine is the driving force behind its spectacular and violent weather, a maelstrom of swirling clouds and colossal storms. Jupiter's atmosphere is a mesmerizing canvas of colorful bands, stripes, and vortices. These features are not driven by sunlight, but by heat rising from the planet's deep interior. As this heat convects upwards, the planet's incredibly fast rotation, a day on Jupiter is less than 10 hours long, smears these rising columns of gas into the distinct bands we see. Embedded within these bands are storms of unimaginable scale. The most famous of these is the Great Red Spot, a gigantic cyclone wider than our entire planet. This storm has been raging for at least 300 years, a persistent swirling vortex with winds over 250 miles per hour, powered by Jupiter's internal heat and rapid spin. Beyond the planet itself, Jupiter reigns over a miniature solar system of its own, with at least 95 known moons. These worlds are just as diverse and fascinating as the planets. The four largest, known as the Galilean moons, are worlds in their own right. The innermost of these is Io, the most volcanically active body in the solar system. Its surface is a chaotic landscape of over 400 active volcanoes, constantly spewing sulfurous plumes high into space. This incredible activity is not driven by internal heat from its formation, but by the relentless gravitational tug-of-war between Jupiter and the other moons. This tidal heating constantly flexes Io's interior, generating immense frictional heat. Just next door to this world of fire is a world of ice Europa. This moon is covered by a smooth crust of water ice, crisscrossed by long dark cracks. Scientists believe that beneath this frozen shell lies a vast global ocean of liquid salt water, kept from freezing by the same tidal heating that powers Io's volcanoes. This subterranean ocean may contain more than twice the amount of water in all of Earth's oceans combined. In 2013, the Hubble Space Telescope spotted what appeared to be geysers of water erupting 124 miles high from Europa's South Pole, providing tantalizing evidence for this hidden ocean. Where there is liquid water, energy, and organic molecules, there is the potential for life. Continuing our journey outward, we arrive at the jewel of the solar system, Saturn. While other giants have rings, none are as spectacular, as complex, or as famous as those encircling the sixth planet. From a distance, they appear as solid, elegant bands, but up close they are revealed to be a breathtakingly intricate system composed of countless individual particles of water ice. These particles range in size from fine dust to chunks as large as a house, all orbiting Saturn at incredible speeds. The Cassini spacecraft, which spent over a decade studying the Saturn system, showed us that these rings are not static but a dynamic, ever-changing environment. The rings of Saturn are like a miniature laboratory for studying how planets and moons form. They are a snapshot of a solar system in a state of arrested development. Within the rings, we can see cosmic processes playing out in real time. The immense gravity of Saturn and its many moons sculpts the rings, creating gaps, waves, and ripples. Small shepherd moons orbit within or near the rings, their gravity corralling the ice particles into sharp, defined edges. Even tinier, unseen moonlets create propeller-like structures as they plow through the ring material, Studying these dynamics helps us understand the chaotic dance of accretion that built the planets 4.5 billion years ago. Beyond its glorious rings, Saturn is home to one of the most intriguing worlds in our quest for life. Its largest moon, Titan. This moon is larger than the planet Mercury, and is unique in the solar system. It is the only other world besides Earth known to have stable bodies of liquid on its surface. However, on Titan, the rivers, lakes, and seas are not filled with water, but with liquid methane and ethane. It has a thick, nitrogen-rich atmosphere, even denser than Earth's, filled with a complex soup of organic molecules. Its surface features mountains made of water ice as hard as rock and dunes made of hydrocarbon sand. The presence of liquid, a thick atmosphere, and complex organic chemistry makes Titan a prime candidate for finding life that is truly alien, a second Genesis. If life exists on Titan, it would be based on a completely different chemistry than ours, thriving in frigid liquid methane instead of temperate water. Discovering such a life form would be one of the most profound scientific breakthroughs in human history. It would suggest that the principles of biology are not unique to Earth-specific conditions, and that life might be a common phenomenon throughout the universe, able to arise in a wide variety of environments. Titan represents a bold new frontier in our search for life. Our voyage now takes us to the far, frozen reaches of the solar system, to the enigmatic ice giants, Uranus and Neptune. These worlds are fundamentally different from the gas giants Jupiter and Saturn. While they have thick atmospheres of hydrogen and helium, their interiors are composed of heavier elements, a hot, dense fluid of water, methane, and ammonia ices. These planets are so distant that the sun appears as just a bright star in their skies. Their weather is not powered by sunlight, but by heat escaping from their deep interiors, creating some of the most extreme and bizarre conditions imaginable. Our only close-up views of these worlds came from the Voyager 2 flybys in the 1980s, leaving much of their nature shrouded in mystery. Neptune, though farther from the Sun than Uranus, is a surprisingly dynamic world. Despite receiving very little solar energy, it boasts the fastest winds in the solar system, with supersonic gusts reaching up to 1,500 miles per hour. These incredible speeds are driven by heat leaking from the planet's core, which gets trapped by its dense mantle. Deep inside the planet, the immense pressure is thought to be so great that it breaks down methane molecules, compressing the carbon atoms into solid crystals. Scientists theorize that it literally rains diamonds in Neptune's deep interior, which then sink toward the core, releasing more heat and fueling the planet's violent storms. Uranus, Neptune's neighbor, presents a different kind of oddity. The entire planet is tilted on its side, orbiting the sun with its poles pointing where most planets have their equators. It spins at an angle of 98 degrees, as if it were knocked over long ago. The leading theory is that this was not caused by a single giant impact, but by a 1-2 punch from two separate, smaller collisions during the chaotic formation of the solar system. This extreme tilt results in the most bizarre seasons imaginable, with each pole facing 42 years of continuous sunlight followed by 42 years of complete darkness. The strangeness of Uranus extends to its moons. It has a tightly packed system of inner moons that appear to be gravitationally unstable. Computer models suggest that their orbits are chaotic, and that in just a few thousand years, a cosmic eye blink, two of the moons, Cupid and Belinda, are destined to collide. This collision could trigger a chain reaction, a domino effect that grinds all the inner moons into dust. The result would be a brand new, spectacular ring system around Uranus. This suggests that rings are not permanent fixtures but are part of an ongoing cosmic cycle of creation and destruction, where moons are born, live, and are eventually recycled back into rings. How do we know all these incredible details about worlds that are millions or even billions of miles away? These discoveries are not the product of guesswork or fantasy. They are the hard-won triumphs of human ingenuity, observation, and relentless scientific inquiry. For centuries, our only tools were our eyes and ground-based telescopes, which slowly revealed the planets as more than just wandering stars. They allowed us to see the phases of Venus, the moons of Jupiter, and the rings of Saturn, providing the first clues that these were other worlds. But to truly understand them, we had to get closer. The dawn of the space age in the mid-20th century revolutionized planetary science. We began sending robotic explorers as our proxies, embarking on a new age of discovery. Missions like the Mariner probes gave us our first close-up looks at Mercury, Venus, and Mars, revealing cratered surfaces and thick atmospheres. The Pioneer and Voyager missions performed the grand tour of the outer solar system, flying past Jupiter, Saturn, Uranus, and Neptune, sending back iconic images and a deluge of data that formed the foundation of our modern understanding of the giant planets. These flybys were fleeting glimpses, but they transformed our view of the solar system forever. Following these initial reconnaissance missions, we sent more advanced spacecraft to stay and study these worlds in detail. Orbiters like Magellan at Venus, Messenger at Mercury, and Galileo at Jupiter mapped surfaces, analyzed atmospheres, and studied magnetic fields for years on end. The Cassini-Huygens mission to Saturn was a monumental achievement, with the Cassini orbiter studying the planet and its moons for 13 years, while the Huygens probe made a historic landing on the surface of Titan. On Mars, a fleet of rovers, from Sojourner to Curiosity and Perseverance, have become our robotic geologists, drilling into rocks and searching for signs of ancient life on the Martian surface. Today, our toolkit is more powerful than ever. Advanced space telescopes like Hubble and the James Webb Space Telescope can study the atmospheres of distant planets with incredible precision, detecting molecules and weather patterns from afar. They complement the work of our robotic probes, providing a broader context and allowing us to monitor these worlds over long periods. Every new mission, every new observation builds upon the last, weaving a richer and more detailed tapestry of knowledge. It is this combination of remote sensing and up-close investigation that allows us to unveil the secrets of our cosmic neighbors, piece by piece. Why do we do this? Why do we spend vast resources and decades of effort to send robots to distant, inhospitable worlds? The answer lies in a deep, fundamental human need to understand our place in the universe. Studying the other planets of our solar system gives us context. It provides a control group for the grand experiment that is Earth. By seeing how Venus became a scorching greenhouse, how Mars lost its water, and how life might exist in the methane lakes of Titan, we learn about the forces that shape all planets, including our own. This knowledge is not just academic, it is critical for safeguarding our future. The study of our solar system holds a mirror up to Earth. The runaway greenhouse effect on Venus is a stark warning of what can happen when a planet's climate balance is tipped too far. The story of Mars, a planet that was once warm and wet but is now a cold, dry desert, teaches us about planetary fragility and the importance of a protective atmosphere and magnetic field. These worlds are not just curiosities, they are natural laboratories that demonstrate the consequences of planetary evolution. Understanding their pasts helps us better model and predict the future of Earth's climate, giving us the wisdom to be better stewards of our own world. Furthermore, the search for life beyond Earth is one of the most profound endeavors humanity has ever undertaken. Finding life, even microbial life on Mars, Europa, or Titan, would revolutionize our understanding of biology. If life has arisen independently twice in our own solar system, it would strongly imply that the universe is teeming with it. We would no longer be able to see ourselves as a singular miraculous event, but as part of a common cosmic biology. This discovery would forever change our perspective on who we are and our significance in the grand scheme of things. It would be a moment of humility and wonder. Ultimately, exploration is an investment in our future. It fuels scientific innovation, drives technological advancement, and inspires the next generation of scientists, engineers, and dreamers. The challenges of space exploration push the boundaries of what is possible, leading to new technologies that benefit us here on Earth. More than that, it gives us a cosmic perspective. It reminds us that we live on a pale blue dot, a fragile oasis in the vast darkness of space. This perspective fosters a sense of global unity and a shared responsibility to protect our only home. The journey through our solar system is a journey back to ourselves, armed with new knowledge, new wonder, and a deeper appreciation for the preciousness of Earth.